In this video, we're going to talk about the beautiful link between the problem of diagonalizing a matrix and the eigenvalue problem. So, let us begin with the eigenvalue problem, which asks to find solutions of an equation like this, where k is a non-zero vector. And if I have several solutions of an equation like this, so let's say some k1 for eigenvalue lambda 1, then k2 for eigenvalue lambda 2, and let's say I've got m of them, then this can be rewritten in the following way as something that I assume you already know from an earlier video. This can be rewritten as a times p equals p times d, where the P matrix is a matrix whose columns are the eigenvectors, and the D matrix is a diagonal matrix whose entries are the eigenvalues appearing in the same order as the columns do, where the column corresponds to the eigenvalue in the order. So lambda 1 is an eigenvalue for eigenvector k1, and so on. By the way, this notation here for a diagonal matrix, these big zeros represent that we've got zero entries everywhere below the diagonal, and the big zero up there represents that we've got zero entries everywhere above the diagonal. Alright, so I'm assuming you already know that a system of equations like this can be also equivalently represented this way with the p and the d that I've written out here. Okay, so that's the eigenvalue problem, to find such k's and lambdas. And if I want to find many of them, I can also ask it as a problem of finding the matrix P and the matrix D such that AP equals P times D. Okay, now what about the diagonalization problem? The diagonalization problem asks to find some matrices P and D, but the equation is slightly different. So the the diagonalization problem asks to find an invertible matrix P so that P inverse times A times P is equal to diagonal matrix. So what's the difference between these two setups? Well, first of all, let's see what is a common thing between those two things. The commonality is that in both cases we're looking at an n by n matrix. So here we've got an n by n matrix, and also here. Okay? Now, in here, the matrix P is not a square matrix. As you can see here, the number of columns m does not have to be equal to n. Whereas here, the matrix P is a square matrix, otherwise it wouldn't be invertible. So these are the differences between the two setups. So to make them more similar to each other, we want to consider a special case of the first setup where we force the m and the n to be equal to each other. Okay? So let us do that. In the case when m and the n are equal to each other, so I'm going to make another partition here, we have the same as before, but now we've got M equals N, and so the matrix P will now be a square matrix with exactly the same number of columns as we had the dimension N for the matrix A. And of course, it is not going to affect the equation at all. The D is the same as before, so that's why I put this arrow there. Maybe I should be less lazy and copy the whole thing down here. There we go. Except that the D is the same as before, except that the M in D is now N, right? Okay, so now that we made that match between the dimensions, what remains is to see how the equations themselves relate with each other. In both cases, D was a diagonal matrix, so maybe we can put this down here as well. D is a diagonal matrix here, and the fact that P is an invertible matrix is self-evident because we're using the inverse of P in the equation. So now let's ask the following question. So everything seems to be similar except that the equations are different, right? So let's ask the following question. What is the link between these equations? Can perhaps from one equation we get the other one and backwards? Well, let's look at this direction first. Can we get from this equation the other one? Look, multiply both sides of this equality by P, right? Then, on the left side, you'll have P times P inverse, which is identity matrix, and so that falls away. So you got AP left, and on the right-hand side, you'll have P times D, which is exactly what we have here. Wonderful, so we can get from left to right. So if the left equation holds, the right equation will also hold, because we can just multiply both sides by P inverse. P is an invertible matrix. We can do that. Sorry, not by P inverse, just by the matrix P. And so we move from the left-hand side to the right-hand side. What about backwards? Can we get from the right-hand side equation the left-hand side equation? Perhaps we should multiply both sides by, on the left side, again, by P inverse. It will work, right? We'll have P inverse AP on the left side, which is exactly what we want here. And then we'll have P inverse PD, and P inverse P is an identity matrix. And we'll have just D then, because identity matrix will fall away. Since identity matrix times anything is that thing back. But we can only do this if we knew P was invertible, right? So the two things correspond to each other as long as we add here on the right-hand side a requirement that P is invertible. So now we get something very, very exciting, like this is so amazing, isn't it? There we go. It is that amazing. You just fall in love with this thing. Why? Because we've just shown that solving the diagonalization problem is equivalent to solving the eigenvalue problem, with the extra requirement that we want the eigenvectors to be giving rise to an invertible matrix when we put them in as columns of the matrix P. So as soon as we can find n eigenvectors that make an invertible matrix, then we'll have this, and therefore we'll have that, and therefore we'll have solved diagonalization problem. And moreover, if we solve the diagonalization problem, we then can get eigenvectors giving rise to an invertible matrix, and hence solve the eigenvector problem. How? The eigenvectors will be the columns of P, and the eigenvalues will be the entries of the diagonal matrix. So to solve the eigenvalue problem, I just pick out the eigenvectors and eigenvalues by picking out the columns of P and the diagonal entries of D. So that's how I move from left to right. On the other hand, if I solve the eigenvalue problem, I'm going to use those eigenvectors. If I solve it in such a way that I have n eigenvectors that makes up an invertible matrix, I can then take those, put them in the matrix, get the invertible matrix, put the eigenvalues in the diagonal matrix, keeping in mind that the order should correspond, right? Here, where are we? I think that's a previous video from a previous slide from a previous video. So we're here. So the order should correspond in the sense that, you see, the lambda 1 is eigenvalue for eigenvector k1, and so on all the way up to lambda m is eigenvalue for eigenvector km. And so if we arrange those eigenvectors and eigenvalues in that order in the matrix P and the matrix D, then out of this equation we get that equation. Therefore, we would have then solved the diagonalization problem. Okay, but what is this additional requirement that we have here? I mean, this is the weird thing here, right? When can we have a column vectors, the eigenvectors, giving rise to an invertible matrix? Well, it turns out, it is beyond the scope of this specific video, but it turns out that this will be so exactly when those eigenvectors are linearly independent. Isn't that remarkable? So it turns out that P is invertible exactly when the columns of P are linearly independent. So in other words, those eigenvectors are linearly independent. So solving a diagonalization problem is the same as solving eigenvalue problem in such a way that we find n linearly independent eigenvectors, because we need them to put them in the matrix, right? That's going to be invertible. Right? And that's the wonder of the comparison of the two topics, the topic of diagonalization and the topic of solving eigenvalue problem.